Hello again. Today's video is about graphing absolute value functions. So we're going to start off our first graph here with the parent function of our absolute value graph. So our parent function, hopefully we recall that the vertex is at 0, 0, the origin. If not, we can easily create a table of values, and that's what we'll do for a lot of these graphs today, is create a table of values that'll show us what points exactly to plot. So it's usually a good idea if we're trying to pick points. Let's pick a couple in the negative direction. So say -3, -2, -1. Let's choose 0, and then again some positive values. So each one of these inputs now, I will now plug into the equation to figure out what the corresponding y value is. So for our first one here, we're picturing what does y equal when x is -3. The absolute value bars is going to turn anything inside of it positive. So in that case, the absolute value of -3 is actually +3, which means that there is a coordinate on our function that is at -3, +3. So we can put a little point on our graph right over there. Let's do the same concept then for the next point, -2. The absolute value of -2 is +2. So again, I will plot that point on our graph. Same idea, I can replace a -1 in for x, evaluate, plot our point. We should start seeing a pattern here. Absolute value of 0 is 0, but then we get this change in direction because the absolute value of +1 is still +1. So instead of going down, our graph gets now reflected and it comes right back up. Absolute value of +2 is +2. And then absolute value of +3 is +3. Now, if we did continue forever and always on, we would see that our function would just keep on going. So we can symbolize that it keeps on going by creating a line. Let's see, red. Let's create a line here. Nice straight line. We can use anything that we have, the side of our, side of our student ID, side of our calculator, side of our notebooks, side of our cell phones. If we happen to have it on our desk, we can use anything that we have that's a straight edge that can go ahead and draw those parts to our absolute value function. Remembering to please put an arrow at the end of the function to again symbolize that these numbers do go on forever and ever. So this is our parent function, like we said, our absolute value graph. We can also think about this as our general equation for an absolute value function. A absolute value of x minus h plus k, where h and k represent our vertex. So for here, our function does not look like it's in that form at all, except where it really is. We just don't have a lot of information. We could really rewrite it really as a 1, absolute value of x minus 0, absolute value plus 0. Now that's the same thing. We don't need to tell anybody to add 0 nor subtract 0, nor do we have to tell them to multiply by 1. So this parent function we know has an origin of 0, 0. And because our a value here is a 1, if we're talking about graphing, that means we plot our origin, and then we can go up 1 and over 1 in both directions to get to our next point. Up 1, over 1, up 1, over 1, and just keep on going. So we can either create a table of values, or we can go ahead and realize the h and the k value, our vertex, and then use our quote-unquote slope, our a value, to get to the next point. So let's take a look at our next equation here. That plus 1, what do you think? Is it an a, an h, or a k value? We rewrite our function. We will see that the plus 1 is really our k value, thus making our vertex at 0, 1, or shifting our graph up 1 unit. From there, if we're recall from the last problem that our A value tells us the direction in which we move. From that vertex, we can go up 1 and over 1 to get to the next point, and just keep moving, up 1, over 1, up 1, over 1, up 1, over 1, till we get this side of our graph. I'll use a straight edge in a moment. We're going to do the same deal in the opposite direction. Start again at your vertex, up 1 and left 1, up 1, left 1, up 1, left 1, up 1, left 1, up 1, left 1. So now let's go ahead and use that straight edge. Nice straight lines over our entire graph. And again, remembering the arrows at the end. Okay, I will go ahead and erase these up 1 over 1s because those are not actually part of the graph. All right, and that's it. So if you want to create the table of values, go right ahead, but it's definitely a lot easier just to realize where your H and your K are, and then use your A value to figure out your points from there. So if we keep going, think at this example here, the -1 that you see, what kind of a transformation does that have on your function? So again, is it an H or a K? In which direction are we moving? Hopefully we realize that the 1 here is an H value, and it actually is going to move opposite of what we think. This tells us that our vertex is actually at 1, positive 1, comma 0. So this is an example of a horizontal shift to the right 1 unit. Again, our A value here is a 1. So we can go ahead and move our graph from there, up 1, over 1, just like we did in the last example. So again, vertex, up 1, over 1, up 1, over 1. Just keep going. Nice straight edge. We'll finish off our graph along with some arrows in both directions. And again, I'm erasing the up 1, over 1 because that's not actually part of the graph. Let's keep it moving. Next one, of course, got to combine everything in our last example here. So we get a version of each one of our transformations. We see a shift to the left or right. We see an up down. We see a compression stretch. And then we also see a reflection. So we have A, H's, and K's that we need to account for. So we can see here that this A value, it's going to do 2 things to our function. Because it is negative, that means our graph gets reflected across the x-axis. Because it is a 2, so I'm just going to denote that that's because of the negative, the 2 is going to be an example of a vertical stretch. So that means that our quote-unquote slope here is going to be 2. Once we figure out our vertex, we can go up 2 and over 1 is our rise and our run, our slope to get to the next points. If we look at the A value, let's see if I can color code this. So green, our A value here, we are looking at that being our left and our right. In this case, because it says x plus 3, that actually means that our graph got shifted to the left 3 units. And then our last piece, that plus 5, actually means that we shifted our function up 5 units. So we have a lot of stuff going on here. Let's start off, got a color code. Let's start off with the location of the vertex. So our vertex is going to be at that H and that K value. So our H and our K here, remember it got shifted to the left 3, so it's actually a -3 for our vertex. And then the positive 5. So that's our H and our K. -3, which is why we have a -3 there. So -3, comma 5. We're going to plot our vertex. And then like we were explaining before, our A value is going to tell us how to move from there. It tells us what our slope is. So since our graph got reflected across the x-axis, it means it's going to be opening down. So for my stretch, I'm going to be going down 2 from the vertex and over 1. Down 2, over 1, down 2, over 1, all the way across the plane of our function. And then do the same deal in the opposite direction. Start back up at our vertex. I'm going down 2 over 1 to the left. And again, and again. Using that straight edge. Nice straight graph with arrows at both ends. All right. Now, if we shift over to quadratics, quadratics are going to work along the same lines. Our A value is still going to be our reflections, our stretch and compressions. If we're graphing in vertex form, our H and our K are still our shifts left, right, up, down, respectively. But we're going to be not having a V shape this time because it's not absolute value, it's quadratic, which is going to be a U shape. So again, starting off with our parent function, let's take a look at our table. So even if I use the same numbers as before, -3, -2, -1, 0, 1, 2, and 3. If I plug each one of those into my function here, y equals, let's say, -3 quantity squared. So -3 squared, or -3 times -3, is +9, which as we can see is a little off our grid. -3, 9 is like somewhere up here. If we did -2 squared, that's going to give us 4. So that fits. -2, 4. -1 squared is a +1. There it is. 0 squared is 0. 1 squared is 1. 2 squared is 4. And again, the 3 squared is off the grid at 9. So remembering when you're sketching this time, we need a U. So please make sure that it looks it. And we should be going through those points. My hand is not as steady as yours is, but try your best, again, like I said, to get through that U shape and try to make it go through the points that you have indicated. So that's our parent function. Now from here, we can do the same kind of shifts that we did with the absolute value. So if we're keeping that idea in mind, that means in this vertex form here that we still have our H, comma, our K. So our vertex here is going to be at 1, comma, -4. So my start is pretty much the same. But I got to figure out from there what are some other values. I no longer can look at the A and just say, oh, it goes up 1 and over 1 in both directions, because that would give me a B, not a U. So let's go ahead and let's make a table of values. It's usually a good idea to try to get 5 points on your grid. So I usually make my T-table so that it shows 5 points. And then I put my vertex in the middle. And then I need to choose 2 points on either side. So to the left of 1, I have 0 and -1. To the right of 1, I have 2 and 3. So I'm going to plug each one of those values in. So y equals -1 -1 quantity squared -4. When I evaluate this, I get 0. So -1, comma 0 is going to be a point on our graph. If I evaluate for 0, I'm going to end up with, looks like -3. So 0, -3 is a point on our graph. I already figured out the vertex from the formula, so I don't have to do that over again. 2 minus 1, quantity squared -4. So again, that gets us -3, and that's exactly what we thought, because hopefully we remember from graphing in vertex form that we have this symmetry. It's exactly an axis of symmetry. It's the imaginary line that goes to the vertex that splits our graph in half. So since we knew 0, negative 3 was a point, positive 2, negative 3 has to be a point. Because we have a point here that's 2 units away from our axis of symmetry, we're going to again have a point here that's 2 units away from our axis of symmetry. So again, sketching my graph as best as I can. Arrows on both ends. Notice here that my graph is going in both directions at an angle because it doesn't go straight up and down. If it went straight up and down, right? Oops. If we went straight up and down here, then we would not have a function any longer. So we need to make sure that our graph goes up at a little bit of an angle to showcase that it goes forever. Right. So get a nice little angle here, and we are good to go. Now, what if I asked you to graph a function in standard form? We would have to be able to figure out some information, right? Because we said standard form is relatively useless, not to hurt its feelings. But the only thing that we can really get from it is that our C value here is our y-intercept. So 0, comma, negative 4, we know is 1 point that's on our graph. Okay. So in order to figure out the vertex from here, the x-coordinate of the vertex, where the axis of symmetry, is located at negative b over 2a. So our b value here is 6, and our a value is negative 1. So in that case, negative 6 over negative 2 is a positive 3. So we know that our axis of symmetry in the x-coordinate of a vertex is somewhere along that line where x equals 3. To figure out what the y value of the vertex is, let's plug that 3 back into our equation and evaluate. So 3 squared is 9, but we have the negative out front, so negative 9. 6 times 3 is 18, minus 4. So we end up with 9 minus 4 is 5. So 3 comma 5 is the location of our vertex. So again, we talked about that axis of symmetry. So since we had our y-intercept here that we found out, it's actually 3 units away from our axis. So we can go 3 units away to the right, and that gets us now 3 points that are on this graph. So we just need to figure out at least one other point and find its symmetric value to get the best shape. So let's pick some number. What do you think is nice and easy? If we're looking between 0 and 3, we already know the value of 0. We already know the value of 3. So if we're choosing between 1 and 2, I tend to think 1 is a little bit easier to work with. So I'm just going to erase here. Let's plug a 1 in and evaluate. So in that case, I get negative 1, a positive 6. So altogether, I get a positive 1, which means that 1 comma 1 is a point on our graph. So that 1, 1 is 2 units away from our axis of symmetry. So if I go 2 units away to the right, I get an additional point, and that is our goal. That is our 5. So again, trying my best to make a U. Arrows in both ends. And that is how we graph a function in standard form. So graph the y-intercept that's given to you at your C value, and then use the equation x equals negative b over 2a to figure out the x-coordinate of the vertex. Plug in to get the y-coordinate, and then pick some number. It does not matter. I could have chosen 1, I could have chosen 2, I could have chosen 4, I could have chosen 5. It really doesn't matter. Just make your life as easy as possible. The last option that we have is trying to graph a function that's in intercept form. So our intercept form, again, tells us the x-coordinates of our vertex. So let's start there. The x-coordinates of our vertex are going to be at 4, comma, 0, and at negative 2, comma, 0. Okay. So I'm plotting the points, 4, comma, 0, negative 2, comma, 0. From this intercept form here, we can, again, picture an axis of symmetry, a line that's splitting straight down the middle between these 2 points. So if we're counting boxes here, hopefully we agree that these 2 x-intercepts are 6 units apart. Half of that would be 3 units. So if I go 3 units towards the middle, starting on the left, I'll have a 1, a 2, a 3. So I end up at positive 1, being where my axis of symmetry shall lie. To figure out what the y value is for the vertex, very similar to the last example, I'm going to plug 1 into my equation. So 1/2, 1 minus 4, and 1 plus 2. So 1/2, this is a negative 3 and a positive 3. So it looks like that's negative 9/2 or negative 4.5. So in our function here, if we had a 1, you go down to negative 4.5. Somewhere over here is going to be the location of our vertex. Very similar to the last example, we do want 5 points. So let's go ahead and plug in a value. So anything between our zeros would be easy. So a negative 1, a 0, a 2, a 3. Any of those would be easy to work with. I tend to think 0 is the easiest option out of all of those. So let's plug in a 0. So let's plug in a 0. So 0 minus 4. We have a 0 plus 2. We have 1/2. So negative 4 times 2 is negative 8. Half of that is negative 4. So that means 0, negative 4 is a point on our graph. Its symmetric point would be at 2, negative 4. Let's again sketch our graph, trying to get that U shape going through those points we just plotted. And that is how you graph an equation in intercept form. Thank you so much for watching.